Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering suffix tree construction. The little caveat is that we won't actually be building the same kind of suffix tree that you would find in an academic textbook or that you would read about on Wikipedia. Instead, we'll be building a simpler data structure that sort of resembles a suffix tree and that can essentially accomplish the same things, mainly because suffix trees, at least the sort of academic suffix trees, are very complicated to implement. But so in this video, we will be building a class for a data structure that looks very much like a tree, like the one that I have here in front of me. And so the suffix tree that you're looking at here is going to be built based on this string, BABC. So basically, you've got a root node, which kind of represents the empty string. And then you've got all of the suffixes in the string BABC that are stored in this tree. You've got the suffix BABC, literally, that starts here, BABC. And then it ends with a little asterisk, because we're also being asked to mark every end of a suffix in the tree with a little asterisk. Then you've got the suffix ABC, which is going to be located here, ABC, with the ending asterisk. Then you've got the suffix BC, which is going to be here, BC, and the little end symbol. And finally, the suffix that is just the letter C, which is going to be here, with a little end symbol after it. So that's going to be what we're looking to create. And then we also want to implement a sort of searching function that is going to be able to search for a string inside the suffix tree. And we want that searching function to tell us whether or not a string is contained in the suffix tree. So let's first start with the creation, right? Actually getting to this data structure here. So if we're given a string like this one, BABC, let's put it at the bottom right here. The way that we can build out our suffix tree is just going to be using a bunch of hash tables or a bunch of dictionaries and Python objects and JavaScript, where every node in the tree, in the suffix tree, is going to be a key in a hash table pointing to another hash table. Okay? And all of the values in the hash table to which it points will be other nodes in the tree whose keys will be a specific letter that comes after the previous letter and that points to another hash table, and so on and so forth. Okay? So if we look at our particular example, right, BABC, the way that we would start implementing this data structure is we would say, let's have an empty dictionary, an empty object, and here we'll represent it with just this root node, which doesn't have anything in it. Or, theoretically, you can say this represents the empty string. And we start iterating through our main string, BABC. And at each index, starting at index 0, we say, let's look at the entire substring starting at this index, and let's add it to the suffix tree. So at the beginning, the first substring that we're going to look at, the first suffix that we're going to look at, is going to be the entire string starting at index 0, BABC. And so what we're going to do is we're going to check whether or not the current letter that we're at in this substring, which starts at 0, B. So as we iterate through all the substrings, or all the suffixes, in the main string, we then iterate through every character of each of those suffixes. So iterating through BABC, start at 0 with the letter B, and we check whether or not the letter B is already stored in our tree. Okay? And here, right now, since this is the very first letter, we can see that B is not stored in our tree. So we're going to add a branch. It's going to point to a node that's going to have the value B. Okay? Now, in code, what this would be is, in this sort of empty hash table here, we would add a key, which would be the letter B, And this letter B would point to an empty object. So, or another empty hash table. So it would point here to, let's say, empty hash table. And then what we do is we move on to the second letter in our current suffix. Current suffix is BABC. The second letter is going to be A. So now perhaps we could put an arrow. We were first pointing at B, and now we are pointing at A. And now we check if this letter A is located in our current node. So one thing I forgot to mention is that as we're building this suffix tree, as we're adding stuff to this suffix tree, we move along with it. So perhaps to make this clearer, let me erase this empty hash table. We know that B is pointing to empty hash table. But when we started, when we had this arrow here in the bottom pointing to B, when we were here, our current node that we were looking at in the tree was the root node. So that's why I just drew an arrow here pointing to the root node. And we checked whether or not B was in this root node, or in the sort of hash table of this root node. It wasn't, so we added it here. And then what we did is we moved our arrow at the bottom to point to A, the second letter in our current suffix, and we move the top arrow here that was pointing to the root node to suddenly point to B. Okay, so let me put it here. Suddenly it points to B. And so now we check, is A, the letter A, in the hash table that B maps to? And we notice that it's not, because the hash table that B maps to is just empty. So we can add A. We add A here. Okay. And then we move our arrow here that was above the A to point above B, the second B. And we move this arrow here that's pointing to B below here to point to A. And now we're looking at this part of the suffix tree. And we ask ourselves, is this B stored somewhere in the hash table that A is pointing to? No, because A is pointing to an empty hash table. Remember, here we could add an arrow that would say empty hash table, right? Let's undo all of that. Since B is not in this empty hash table, we can add a node here that's going to point to B. And again, we move our arrows. This one points to the last letter in our current suffix, which is going to be C. And this one is going to point to the node that we just added, B. So now we check if C is contained in this the hash table that B maps to. It's not, because it's an empty hash table. So we add an edge here that points to C. And now we move our arrows again. This one moves out of the suffix. We're done. There's nothing more to explore in the suffix. We've added the entire suffix. This arrow points to C. And because we've added an entire suffix, an entire string or substring, whatever you want to call it, we add this final node that is just an asterisk symbol that kind of tells us, it marks the end of a string here. Okay? Then we're going to erase all of our arrows. And remember, at the beginning, we said we're going to iterate through all of the suffixes in the string. So now we can kind of erase this part of the suffix here and say, let's look at the suffix starting at A, the suffix ABC, right? And for this string here, let's add all of the suffixes. Or let's add all of the characters. We're going to add the suffix in the tree, and let's add all of the characters. So we start at A. So we put our arrow at A, and now we go back to the root node of our tree. So we put our arrow here at the top of the tree. And we say, is A contained in the hash table that this root node maps to? No, it's not. All that there is in this hash table that this maps to is B, right? There is no A. So we add A here. And then we move both of our arrows. We move the top arrow to point to A, and we move this arrow to point to B. Now we check if B is here. It's not, right? This points to an empty hash table, so we can add B. Now we can go a bit quicker. We can move the arrow again, move this arrow again. We've got C, so we're going to add C to this node, and then we are out of the string. So if we move both of our arrows, we notice that we've added the entire suffix, so we add an asterisk. Boom. And now we know that we've got a substring or a suffix in this tree that is A, B, C. So now we can erase our arrows, and we can explore the next suffix, which is going to start at B, so it's going to be BC. We can put both of our arrows, and this is where the sort of beauty of a suffix tree appears. Instead of adding another node for B here, we already have one that exists at this node here. Therefore, we can say, let's move our arrow to point to this B here, and we don't need to add anything else, okay? And then we can say, we can move our next arrow here to point to the next character, C, and we can check whether or not there's a C somewhere here. And there isn't, there's only an A. This B only points to an A, right? The hash table that this B points to only has the letter A. So we're going to add C, right? We're going to add C. And then we move this arrow, boom, here. We move this arrow out of the string, and we see that we're done with the suffix. So we add an asterisk. So again, to repeat, the important part here is that because B was already contained in the suffix tree, we didn't re-add a node pointing to B. We just kept this node pointing to B and made this one point to C afterwards. And so now the final thing is we've got the final suffix, which is just going to be the letter C. And I'll put the arrows for the sake of the example just to show you, right? We have the two arrows. Notice that there is no C in the hash table that the empty node points to. There's only B and A. So we're going to add a node here that's going to point to C. And then finally, this node is going to point to the asterisk symbol. But now what I want to say is I want to show you how nice this would be if we were to add a bunch of other strings. Imagine we had a much bigger substring or string, input string. Now, if we were to keep adding other suffixes, things might become a lot easier because we might already have constructed or stored their values, right? So like here, imagine we were adding a string called ABD, a suffix consisting of the letters ABD. Well, all that we would have to do would be check whether the first letter A is contained in the root node's hash table. Yes, it is. It's here. Then check if the letter B is contained in this node's hash table. Yes, it is. It's here. And then check if the letter D is contained in this node's hash table. No, it's not. There's only the letter C. So we would add another arm to the tree here, make it point to D, and then make that point to an asterisk, right? And then imagine we have the string ABDF. We would also start at the root node, go to A, go to B, go to D, and then add an F, like this, right? And then add an asterisk. And so that's kind of the beauty of the suffix tree, is that we can reuse or of this data structure that resembles a suffix tree, is that we can reuse nodes that have already been added to the tree and that kind of represent the start of a suffix. So now let's cover searching, and then we'll get into space complexity analysis and time complexity analysis. So how do we search for a string in the suffix tree? So our initial string was BABC, and let's say that we were looking for the string ABC, okay? Or instead, let's say we were looking for BABC, because we kind of just did ABC with my other example. But if we were looking for BABC, all that we would have to do to find whether or not BABC is in our original string is look at the suffix tree, start at the root node, and say, is the letter B contained in this root node? Yes, it is. Boom, we're here. So we start here. Is the letter B contained in this root node? Yes, it is. Great. We move it here. Is the letter A contained in this node? Yes, it is. It's here. Is the letter B contained in this node? Yes, it is. It's here. Is the letter C contained in this node? Yes, it is. And then, do we have an asterisk right after that? Yes, we do. So BABC is a string, is a suffix of our original string because it is contained in this suffix tree. Now, another example is, imagine we were looking for the string BAB. Is the string, this is a kind of a trick question, is the string BAB a suffix of BABC? It's not a suffix of BABC because it's a prefix of BABC, but not a suffix, right? Because it doesn't end with the final character of the string. So if we search for BAB in the suffix tree, we should not find it. And now, how would we know that it's not in there? Well, we would bring our arrow to the top right here. We would look for the letter B, the first letter of the string. B is here. Then we would look for A. A is here. Then we would look for B. B is here. So we would have the string BAB. But then we would look for an asterisk. Is there an asterisk? Does B point to an asterisk here that would mean that that would mark the end of a string? Because it doesn't, we would return false. BAB is not a suffix of BABC. Okay? And the beauty of this is that what that means is that once we have the suffix tree created, we can build or we can search for any string in our original string that makes up the suffix tree in O of n time, where n is the length of the substring that we're looking for. Or perhaps we should call this O of m time. So let's write this down, right? And perhaps maybe let me give ourselves a bit of space here. I'm going to make this a lot smaller. 1 second. Why is this not moving? Okay, we're grabbing this and let's make it smaller. There you go. So, searching. Time complexity is going to be equal to O of m time, where m is the length of whatever string we're searching for in the suffix tree. Because remember, let's say we're searching for BAB. All that we have to do is start at the root node, go to B, go to A, go to B, check if there's an asterisk, and we're done. All that we've done is iterated through the string itself, BAB, and done like constant time operations to check whether or not it's in the suffix tree. And if we're looking for a string that happens to, break at a certain spot because there is no character, like let's say we were looking for BAXB, it would take even less than O of n time because we'd start at B, then go to A, and then we wouldn't find X, and so we'd be done. But so overall, the time complexity is going to be O of m, where m is the length of the string that we're searching for. And then the space complexity is going to be O of 1, because we're not storing any extra space, right? We're iterating through our string, the string that we're looking for, BAB, And we already have our suffix tree constructed, so we're not storing any extra space. Now, creation, on the other hand, let's write it down. Creation is going to take, in time, O of n squared, where n is the length of the input string that we're looking for. And the reason being is we're iterating through all of the suffixes and then iterating through all of their characters. So we're kind of doing like a double for loop. And you can imagine with this string, this input string BABC, right? We were looking at BABC, ABC, BC, and C. And for each of those, we looked at all their characters. So we looked at B, A, B, C, A, B, C, B, C, and C, right? And so that, those two sort of for loops, right, that we're going to use to do that is going to converge to O of n squared time. And we're not performing any sort of complex operations at each of those characters. So, we're performing constant time operations of adding value to a hash table, for instance. But so that's why we've got a time complexity of O of n squared time. Now, here's where I'm going to note that a real suffix tree, you can actually build a real suffix tree in O of n time with some really complex algorithms like Yukonen's algorithm. But, they take a lot more work to build and they look a bit different. Then, in terms of space complexity, we're going to talk about how much space does this suffix tree kind of take, right, require. And that's also going to be O of n squared, at least in the worst case and on average. In other words, if there aren't too many repeating characters, we're going to be storing almost all the characters of all of the suffixes. In our example, BABC, the only character that repeated itself was B, right? So that's kind of the only node that we had to avoid. But otherwise, we're storing every character in the suffix tree. The example case in which we'll only use O of n space would be if we had a string that consisted of only the same character. So like if our string were T, 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 what would happen is we'd literally have like a suffix tree that would go down like this. It would just be a straight line, T, 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 with a bunch of asterisks, right? All of these would have like an asterisk branch coming out of them. But so that would be O of n time. The worst case, though, is going to be O of n squared time, and probably the average case, where there are only a few repeating characters. So that's it. This is how this suffix tree-like data structure works. This is how you can construct it. It's a super useful data structure for any kind of problem that involves, finding strings, searching for strings, matching strings. So try to remind yourself whenever you come across a question like that involves strings that you might want to use a suffix tree, and try to remember how to build it, because it might come in really handy to know at least how to search through it. That's it for the conceptual overview. Let's dive into the code walkthrough to see how we can actually build it out. All right, so we've got our suffix tree class defined. It's got a root property, which kind of represents that root node, which was sort of the empty string. It points to an empty Python dictionary, JavaScript object, basically some kind of hash table data structure. It's got this end symbol property that is the asterisk that we're going to want to have at the end of every suffix in the tree. And then it's got this populate suffix tree from function, which we're going to implement, which is essentially going to be the creation method, right? And that's going to be called on instantiation, and it's going to take in whatever input string we give it, right? The string that we give to the suffix tree class. So populating the suffix tree from a string is going to involve iterating through all of the suffixes of the string and adding them one by one to the tree, just as we did in the conceptual overview. So to iterate through all the suffixes, what we can do is just say for I in range len of string, right? A simple for loop through every character in the string. And then we can kind of call a helper method, which we'll define in a second, which is going to be insert substring starting at this index, right? Insert the particular suffix that we're currently looking at. So we'll do self.insert substring starting at, and we'll pass index I as well as the string, the actual string from which we're getting a substring. And so now we can define a new function, which is going to be called insert substring starting at. It's going to take in an index. It's going to take in a string, which we just passed it, right? The input string. And so this is the actual method that inserts a string in our suffix tree, right? This is going to go through the process of checking whether or not a certain character is already stored in the tree, and so on and so forth. So the first thing we'll do is we'll define a node variable, which is going to represent kind of the current node that we're looking at. This is going to represent the arrow that we had, the green arrow that was pointing at a given node in the suffix tree in the conceptual overview. So we'll start it at the root node. So node is going to be equal to self.root at the very beginning. And then we can start iterating through all the characters in our substring. For j in range, starting at I, going all the way to the end of the string, so from I to length string, the current letter that we're looking at is going to be equal to string at index j. And this, right, is going to represent that second green arrow that we had that was pointing to a given character in the string, or in the suffix. So letter is going to be equal to string at index j. And then we're going to check whether or not the letter is stored in the suffix tree at the current node that we're at. So we're going to say if letter is not in our current node, and remember, our node is just a Python dictionary, a hash table, right? So if our node is not a key, if our letter is not a key stored in our current node, which is self.root at the beginning, then we say node at letter is going to be equal to an empty hash table, an empty JavaScript object. Okay? Otherwise, if the letter is in the node, just don't do anything. And all that we do after this is say node is going to be equal to node letter. So we update our green arrow that was pointing to nodes in the tree. Okay? So it's important to understand what's happening here, right? We start at the top of our function, insert substring starting at, we start by declaring our node to be the root of the tree. And then we start iterating through all the letters in our string, right? Letter is going to be equal to string at index j. And if the letter is not in our current node, then we create a new node, right, for that letter. Node at letter is going to be equal to just an empty hash table. Otherwise, if it is in the node, then we don't do anything. And then in either case, we continue traversing the tree by updating our current node to point to the node of the current letter that we're at, which is either an existing node or one that we literally just created here on line 16. And then once we are done iterating through the entire substring, that means that we've either added a bunch of nodes or maybe we've visited a bunch of existing nodes up until the end of our string. And at this point, we want to add an asterisk at the end to really denote that we have a substring here, a suffix. So we're going to say node of self.end symbol is going to be equal to true. And here you can put whatever value you want. I'm just using true because it kind of makes sense, right? The end symbol, which represents the end of the string, is true. So notice that this line 18 here happens outside of the for loop. In other words, once we're finished iterating through our entire substring and adding or traversing the tree and adding nodes or not adding nodes, whatever the node at the end is, we add an end symbol to it and mark it to true. And of course, if there are sort of overlapping strings, doesn't really matter. You're just overwriting this. But in either way, you wouldn't have an overlapping string. You would never have an overlapping suffix because you'd always be because of the nature of suffixes, you would never arrive to a point where you're overlapping an end symbol. At least I don't think so off the top of my head, but either way, it wouldn't really matter. And so then we can write our contains function, which is going to be surprisingly, or maybe not surprisingly, but I guess it's kind of funny that it's going to be extremely similar in logic and in implementation to the function that we just wrote, right? So to check if a string is contained in our tree, in our suffix tree, we're going to declare a node, which is going to start at the root, self.root, and then we're going to say for-letter in string. In this case, we don't need to keep track of the indices, right? Because we're not starting at an index. So for-letter in string, if letter not in node, then return false. So if our current letter is not in the current node, then that means that this string is not contained in the suffix tree. And otherwise, just update the node to be node.letter, right? Keep traversing down the suffix tree. And then at the end, right, once we're done, like assuming that for every single letter in the string, we have never hit this if condition, which would have returned false, meaning for every letter in the string, the letter was in whatever current node we were at. Then at the end, to make sure that we are dealing with a string that is in the suffix tree, we want to return self.end symbol in node, right? Return the assertion that our asterisk is in our current node, which represents the final letter in our string. If the end symbol is in that node, that means that we did indeed add this particular string ending in this particular letter in the suffix tree before. If it's not, then we've just found a string that is a substring of another one in the suffix tree, but it doesn't actually represent a full string ending in this letter. Okay, so this is why we return the fact that self.end symbol is in the node. And so as we mentioned in the conceptual overview, this particular method, the creation method, is going to run in O of n squared time, where n is the length of the input string, and it's going to run in roughly O of n squared space, where n is the length of the input string, except in the case where the string is just the same character repeated over and over again, in which case you might have a space complexity of O of n, but that is more the exception rather than the rule. Typically, you won't have too many repeating characters. And the time complexity would definitely not change because you'd still be doing these sort of double for loops, right? For I in range len a string, and then for j in range here. And then the contains method is going to run in O of m time, where m is going to be the length of this input string, right? The input string that you're looking for. And O of 1 space, because you are not using any extra space, right? You're just keeping track of this node variable that doesn't really matter. That's constant space. And in terms of time complexity, you are iterating through every letter out of m letters in the string and just doing a simple check here. That's an O of 1 operation. So we get O of m time, O of 1 space. That is it for this video. I hope that now you understand how this data structure that sort of resembles, at least conceptually, a suffix tree works, how it can be really useful when you're looking for strings, especially because of this contains method, right? This contains method is kind of the beauty, because typically, if you were looking for whether or not a specific string was in another string, you'd have to do, probably 2 for loops, and it would be ugly unless you applied some kind of fancy string matching algorithm, but this is one way to do it. Like I said, that's it for this video. I hope it was helpful, and I will see you in the next one.